So here we can see that diagonal elements are variances, and we can see even covariance matrix is a symmetric because Aij is equal to Aji, because the relation between x2 x1 and x1 x2 both are same. So covariance between x1 and x2 and covariance between x2 x1 will be same. So these both the values will be same. So that's why here, as upper triangular matrix is equal to almost lower triangular matrix, then we are calling this matrix as symmetric matrix. So next, it is a positive semi-definite matrix. We have seen why it is positive, because y means there will be considering only the magnitude. So it is called as positive semi-definite matrix. Covariance is a real symmetric positive semi-definite matrix. All eigenvalues must be real. Eigenvectors corresponding to different eigenvalues are orthogonal. Orthogonal means nothing but perpendicular to each other. Like vectors, eigenvectors corresponding to different eigenvalues are orthogonal. It means that for this covariance matrix, if you are finding out eigenvalues, and for each eigenvalue, if you are finding out like eigenvector, so for one lambda one, if we get like some x1 bar or some eigenvector, like we may call it as EV, we will call it as eigenvector. Like for lambda 1, if you are calculating EV1, then for lambda 2, if you are calculating EV2, then EV1 and EV2 will be perpendicular to each other. So that's what one of the property of this covariance matrix. Eigenvectors corresponding to different eigenvalues are orthogonal. So eigenvalues are greater than or equal to 0. Covariance matrix can be diagonal. So we can make it into a diagonal. So covariance matrix is equal to PD P transpose. We'll see. So here nothing but if you are decomposing the covariance matrix into like three matrices, P matrix and D matrix and P, here nothing but if you are finding P and then D, we can find out like P transpose. Then if you are multiplying like P, D and PT, then this is the covariance matrix. We are decomposing it because for if you want to make the matrix operations easily, then we decompose any like complex matrix into different constituent parts for our easy matrix operation. So that is called as decomposition. We will also discuss in this today's session regarding decomposition, because decomposition is used in a SVD. Without decomposition, we cannot go for SVD, like single value decomposition. The name itself says that singular value decomposition. So here we have seen like positive correlation, negative correlation, and no relation. Correlation is one more thing we need to know. Pxy is correlation of xy is equal like co xy divided by square root of variance of x square root of variance of y. We know how to calculate the x component and y component of the variance, and then if you are square rooting it, and then if you are in the numerator, if you are taking covariance of xy, then we will get the correlation matrix. Correlation. It is a scalar value. We will get a scalar value correlation. So usually the correlation of xy will be in between -1 to +1. It means that it will be 0 to 1 and 0 to -1. So we can say by perfect positive correlation, that is 1, and high positive correlation 0.8, low positive correlation no relation, and low negative correlation, high negative correlation, and perfect negative correlation. So this can, like we can go for good fit line or line of good fit. In this case, the line of good fit passes through all the data points, and here we may get the least distance from the data points, and in this case somewhat we will not get the least distance, because as they are scattered in all the ways, and here we will not get any relation, because if you are going for a line of good fit like this, then it will not be like equal from all the points. So that is not a good fit. But in this case we can go like this, but it has got like low correlation. So here high negative correlation. So if you are taking a line like this, then it will have least distance from each point. So here is a perfect negative correlation. Whatever the line of regression or good fit we are taking, it will pass through all the data points. So -1 and 1 almost will not get like this anywhere, because we'll get either like this or in between from 0.5 to 0.8 we'll get either negative or positive values for any data point. If you are getting one, then it is very good because we can directly get a linear regression line for our algorithm. So actually we have like PCA. I have shown this. So we'll move further. Okay. Is the screen visible? Okay, thank you. So in this case, we have seen like what is covariance and a covariance matrix. Now we are going to, with the help of covariance matrix, we'll go for principal component analysis. Whenever we are calling either principal component analysis or like a singular value decomposition or least square, we are not least square. These two are the widely used methods like principal component analysis and a singular value decomposition, where we are trying to decrease the dimensionality of our given matrix. That is, if the data point, if the data set has like m by n matrix, then we will go for try to reduce the number of columns so that for our matrix operations, if there are any columns which are not like good fit or which have no correlation between or between each other, then we will eliminate those kind of columns. So we will find out what is the correlation, and if the value is almost 0 or equal to 0, like 0.2 or 0.1, then we will eliminate those kinds of columns for easy matrix multiplication, because they will not lead to any good fit for our line. So we have like principal component analysis, PCA we will call it as for short, is a method for reducing the dimensionality of data. As I said, we are here we are going to like if there is a data of, with like m columns, m features is projected into a subspace with m or fewer columns while retaining the essence of the original data. So whatever the essence of the original data, we need to keep that and we need to reduce the columns, because if there is like I said, if the some of the correlation between some of the columns is very less, then we need to eliminate, we can eliminate those kinds of columns. Now PCA is an operation applied to a data set represented by a n by m matrix A. So that results in a projection of A, which we will call it as B. So here what we are doing, we are trying to calculate another matrix which is B, which we are going to call it as a projection of A. So if you can directly calculate actually with the help of Python, B is equal to PCA in braces. If you are keeping A, then it will directly give the matrix. Like a projection of A, it will assign for B. The first step is to calculate the mean values of each column. So as we have discussed, like each column represents, we have taken an example like m by n matrix, where m features are there and n students are there, and n so each column represents some student. Then similarly, we need to find for each student the mean for different for the whole column. So next we will need to center the values in each column by subtracting the mean column value. That is nothing but C is equal to A minus M. So here the next step is to calculate the covariance matrix of the centered matrix C. So we are going to first find out C, that is nothing but A minus mean. This is A, and what is M? It is a mean matrix of all these points. We are going to calculate a mean matrix, and if you are subtracting it from the A, we will get a C matrix, that is centered matrix. Now, with the help of centered matrix, you can go for like calculation of covariance matrix of the centered matrix C. So, as we have seen in the previous slides, that how to go for a covariance matrix. Even with the help of Python, we can directly calculate the covariance matrix. If you know the syntax for that is very easy to calculate the covariance matrix in Python. Next, we have like correlation is a normalized measure of the amount and direction, like positive or negative. As we have seen, the correlation like positive, negative, and no relation. So the two columns change together. So covariance is a generalized and unnormalized version of the correlation. So, so that is all. Yes. So V is equal to covariance of C. So we can get the what is V here? Now covariance matrix is represented by V. Finally, we can calculate the eigen decomposition of the covariance matrix V. This results in a list of eigenvalues and a list of eigenvectors. Now we are going to, we have got like covariance matrix. For that we go for like calculation of eigenvalues and eigenvector. We will represent by values comma vectors is equal to eigen eig v. So after getting that, we will go for B. Well, what is B? It is a projection of A. So like B, that may be discarded, A of total. So here other matrix decomposition methods can be used, such as singular value decomposition or SVD. As generally the values are referred to as a okay. P is equal to B transpose A. So we have calculated B from here, from the selected eigenvalues and vectors. We are calculating the projection of A to the B, and we are finding out B transpose and multiplying it with A. So where actually A is the original data that we wish to project, and B transpose is the transpose of the chosen principal component. So here whatever we are choosing like principal component, if we are deleting or we are dropping some columns and we are keeping some of the columns. So whatever we are choosing to retain the columns for the essence of our original data, those columns are called as principal component. So with that, we are finding a like matrix B, and we are finding out B transpose. If we are whatever with the like principal components transpose matrix, we are finding out and we are multiplying it with the original matrix, then we are getting a like a projection, that is P. P is the projection of A. This is called the covariance method for calculating the PCA. Although there are alternative ways to calculate it, but we will use this PCA. So to find, we'll use this method to find out PCA for any given data set. Now here we have like calculate principal component analysis. Like we can do these operations in the Python, and we can go for the calculation of PCA. Like we need to import NumPy. From NumPy we can import array and mean and covariance, and from linear algebra we can go for importing EIG, that is eigenvectors and eigenvalues. So here A is a given matrix. So with that, we can go for finding out first what we need to do. We need to find M, and A minus M gives us T, centered matrix. So we will go for that. M is equal to mean A transpose X is equal to 1. So we will get a M. Then, so X is equal to 1 means nothing but we are going to do the operation along the columns, because as we have seen that M is a what is this M? The first step is to calculate the mean values of each column. So for in Python, for selecting the columns, we use this notation, that is axis is equal to 1 for selecting column. If axis is equal to 0, it means that we are selecting the rows. So we do not want rows to be calculated with the mean. We wanted to calculate along the columns. So we axis is equal to 1. Then C is equal to A minus M. Then we will go for the calculate the covariance matrix of central matrix. B is equal to covariance of C. Dot C means nothing but transpose. factorized covariance matrix like values comma vectors is equal to eigenvectors. So here print vectors and print values means it is going to give us the what are the eigenvectors and what are the eigenvalues for the V matrix. That is covariance matrix. Next, how to present.
Yeah, just hold on, Ramu. So all of you, one thing you have to understand is that here just to get the concepts, you people need not go into too details about because most of the Python libraries or R libraries or any language libraries, they have the what to say, they will calculate and give it to us. But whenever any interviews or anything we are going through this part, right? If you are able to tell the concept, it is good. Like in interviews and all, like what is the, they will definitely ask the concept, just that get the concept thoroughly, and then the rest of the formula and all things can be applied through directly. Libraries will be available directly, you can get that. Okay, go ahead, Ram.
Okay, so here we'll get the output like this. Here what is this means, M matrix. Then we have like this is what is this, covariance V, not V. No, this is print A. This is print A, and this is okay. These are the eigenvectors, and this is the eigenvalue, and this is nothing but P. So here P represents what? PCA. So this is how we will go for with the help of NumPy we can calculate the PCA, and we have like scikit-learn. With the help of this also we can go for calculating the PCA. So we can go through this as everybody has got this. So I will move on to the further topic, that is SVD. So in SVD, what we need to know means we need to know actually what is decomposition. So singular value decomposition. So here, what is decomposition means nothing but we are if we have a matrix of like m by n order, then if it is very large like m by n, then if the matrix operations are very like a hectic even for the computer, then we need to go for decomposing it into constituent parts so that even the computer or machine can make the matrix operations easily. So for that purpose, we will go for the use of this concept, that is matrix decomposition. So here many complex matrix operations cannot be solved efficiently or with stability using the limited precision of computers. So matrix decompositions are methods that reduce a matrix into constituent parts that make it easier to calculate more complex matrix operations. So we have like as I said, it is matrix decomposition is to do the matrix operation easily. For that purpose, we will go for the decomposition. We have like three methods: LU decomposition, QR decomposition, and Cholesky decomposition. So whenever we have like any matrix given to you and you need to perform decomposition, if it is a square matrix, then we will first go for LU decomposition. So if it is not a square matrix, if it is some M by N order matrix, then we will go for QR decomposition. And we have like even Cholesky decomposition, which can be used either for square or even for rectangular matrices. So we have seen what is here. L means nothing but a lower triangular matrix. U means upper triangular matrix. So how we are going to find this lower triangular matrix and upper triangular components with? We have like we need to follow some of the we have seen like in for finding out A inverse, we have performed some of the row or column operations, and we have got like A inverse. So similarly, we need to do some of the row or column operations in this to find out the L, that is lower triangular matrix, and even upper triangular matrix. Then what L into U is nothing but if you are multiplying L into U, we will get the original matrix A. So that is nothing but LU decomposition. As I said you, this is for a square matrix, and LU decomposition is found using an iterative numerical process and can fail for those matrices. Actually, this LU decomposition has some particular steps to be followed for finding out lower triangular matrix and upper triangular matrix. But this process will fail, or this step-by-step procedure fails when the matrix is easy to get the lower triangular matrix and upper triangular matrix. Uh, so in those cases, it will fail. Fail for those matrices that cannot be decomposed or decomposed easily. So if a matrix, if it is cannot be decomposed or if it is decomposed easily, then this step-by-step procedure fails. So we need to see whether either it can be decomposed or whether it can be easily decomposed. So the variation of this decomposition that is numerically more stable to solve in practice is called LUP decomposition or the LU decomposition with partial pivoting. So the rows of the parent matrix are reordered to simplify the decomposition process, and the additional P matrix specify a way to permute the result or return the result to the original order. So if you are multiplying these all the three like a partial pivoting matrix, then we will get nothing but A. If you are unable to do LU, then we will go for partial pivoting. So this can be done with the help of NumPy and SciPy. Linear algebra, we can go for this LU decomposition. Quickly, we will go on to this QR decomposition. So as I said you, if the matrix is not a square, then we will go for this QR decomposition. Actually, why we need to learn like LU decomposition or QR decomposition or Cholesky decomposition is in singular value decomposition, that is SPD. If you know what is how to decompose, then only we can go for implementing the SPD on any data set. Like QR decomposition is n by m matrix, where Q is a matrix with this is where Q is m by m. If you have got like n by m matrix, right? N by m. Then Q represents m by m matrix and R represents m by n matrix. R represents a upper triangular matrix with the size m by n. So here we will get m by m. Like here. Okay, let me see. So here, what is Q? Q is of order m by m, and R is of order like m by n. So what we will get with the multiplication of these two, we will get like Q into R. So we will get a matrix that is which is equal to n by m. So that's why we are decomposing this A into two matrices, where Q is m by m, which is a square matrix, and R is a m by n. Here m is equal to m columns in Q is equal to m rows in R matrix. Then only matrix multiplication is possible. So that's why we are doing like this, and we are going to find out A. So this is also one of the decomposition, that is QR. When we will go for this means if the matrix is not square, then we will go for this matrix. So we have like we can do the same thing with the help of NumPy. We can go for a QR decomposition. We have like next Cholesky decomposition. So this is for square symmetric matrices where all the values are greater than 0. So if you have any given matrix and if all the values are positive and they are greater than 0, then only Cholesky decomposition is possible. We have like lower triangular, L is nothing but here lower triangular matrix, and L transpose is nothing but transpose of L. Then if you are multiplying L into L transpose, we will get the original matrix, that is A. So if you are the decompose can also be written as the product of the upper triangular matrix. So if you are unable to get lower triangular matrix, then we can easily, if you see after seeing the matrix that upper triangular matrix with the row operations or column operations is easy to get, then we can for Cholesky decomposition even we can use the upper triangular matrix for for decomposition, like U transpose dot U, that is UT, you will get A matrix. So why we are splitting means if A is unable to perform matrix operations are difficult to perform in A. If you are using somewhere like if you are multiplying with A into some X bar, another eigenvector or something. Then if it is not possible, then we go for using, in place of A, we use ut dot u into that x bar. So that is the use of this decomposition. Uh, so even we can go for that. So let's see decomposition, and even we have like eigen decomposition. I will we can quickly go through this. We know that a v is equal to lambda v, where v is eigenvector and lambda is eigenvalue. We know that, and here comes the picture. A can be written as q, um, and this is lambda q transpose, where q is a matrix comprised of the eigenvector. Now, what is q? If you have like a matrix, if you're able to find like lambda, if you got like two lambda, and if you have got like two eigenvectors, if you are combining like each column represents the each eigenvector, then that matrix is nothing but q. And what is a lambda means? Lambda is nothing but, here this is lambda, it is uppercase lambda, and here the diagonal matrix comprised of eigenvalues. Now, what is lambda matrix means? Here the diagonal matrices will be eigenvalues, and qt, everybody knows this is a transpose of q. So q into lambda matrix into q. Here we are using, in this q we are using eigenvector, and in lambda we are using lambda values, and here q transpose, if you are multiplying these three things, we will get the original value. So this is eigen decomposition, where we can sometimes even we can go for, if we have already calculated eigenvalues and eigenvector, if we wanted to perform some matrix operation on A, if it is not possible to do directly on it, then we can go for using this decomposition. So we have know how to find out eigenvalues and eigenvectors, right? Eigen decomposition by using NumPy. So you can go through all this. Next week, singular value decomposition. As we have said, whenever it is like feature extraction, if you have got any, if you have been given any data set, then you need to consider only some of the features which are actually which will be which will keep the essence of the original data. And if you are able to remove some of the columns from the matrix, or which have low correlation between other columns, then we can remove those columns. So here what we are doing, we are extracting some of the features from the given data set. So for that purpose, we can go for either PCA or SPD. So these two are most widely used for dimensionality reduction for any given data set. If you have any large data set, and if you know the correlation between each column, then based on the correlation values, we can go for, if the correlation values are like 0 or 0.2 or 0.3, we can remove those kinds of columns, and we can form a new matrix, or a new matrix which is order of, if m by n is the order of the original matrix, then we can go for another matrix which has like m lesser than m and n lesser than m, m by n matrix. So for that dimensionality reduction, we use two methods, that is PCA and singular value decomposition. So here we will use, as we have discussed singular value, what is decomposition, we will see what is singular value. So everybody knows what is decomposition now. Here we will go, we'll see what is singular value. So here matrix decomposition, also known as matrix factorization. So decomposition can also be called as factorization, involves describing a given matrix using its constituent element. Constituent elements, like if you are going for eigen decomposition, A is written as Q lambda Q transpose. So Q lambda and Q transpose are called as constituent elements. So perhaps the most known and widely used matrix decomposition method is the singular value decomposition, or SVD. All matrices have an SVD which makes it more stable than other methods. So such as the eigen decomposition. We have seen earlier what is eigen decomposition. So even it is more stable than other methods. So that's why we are using this SVD. We will not go for eigen decomposition. So as such, it is often used wide array of applications including compressing, denoising, and data reduction. So denoising and data reduction and compressing is nothing but whatever I have said you, like feature extraction, or which are not which have like no, they are no use in our those kinds of columns are not used for our data set. Then we'll either compress them or denoise them or the data reduction. Everything is something like same. In this tutorial, you will discover the singular value decomposition method. So actually, we will see what is singular matrix, singular value decomposition. So SVD for short, a matrix decomposition method for reducing a matrix to its constituent parts in order to make certain subsequent matrix calculations simpler. So as I said, you whenever we are coming across decomposition, it means that the matrix operations or calculations, to make them simple or easier, we'll go for decomposition. The same thing is said here. For the case of simplicity, we will focus on SVD for real valued matrices and ignore the case for complex numbers. So real numbers means negative and positive values will come, but no complex means no I will not come into picture here. Imaginary numbers will not come into picture. I is nothing but I is equal to square root of -1. So that will not come into picture here. Real numbers. So next, the singular value decomposition is a highlight of linear algebra, and most of the times we will use this SVD only. Like we can see here, A is the real n by n matrix, and we wish to decompose A into U. U is nothing but a m by m matrix, another square matrix, and sigma is an m by n matrix. It is something like similar to a QR decomposition, and Vt is the transpose of V, and V is n by n matrix, where T is the superscript. No need to worry. I will move further. The diagonal value, here comes the picture. The diagonal values in the sigma matrix are known as the singular values of the original matrix A. So the columns of U matrix are called the left singular vectors of A, and the columns of V are called the right singular vector. So what is a singular matrix? Singular matrix is nothing but where we cannot find out inverse forward matrix and the determinant will be 0. Then we will call it a singular matrix. Now, how we are decomposing it into a singular matrices? We are decomposing the original given matrix into some singular matrices. Then we are calling it a singular value decomposition. So, and the columns of V are called the right singular vectors of A. So we are trying to make left singular matrix and right singular matrix from the original matrix, and we are forming another sigma, that is the diagonal values. With the diagonal values, we are going for another matrix which is a singular matrix. So every rectangular matrix has a singular value decomposition, although the resulting matrices may contain complex numbers and limitations of floating point arithmetic may cause some matrices to fail to decompose neatly. So here we'll move further. The SVD is used widely both in calculation of other matrix operations such as matrix inverse, but also as a data reduction method in machine learning. SVD can also be used in least square linear regression, image compression, and denoising data. The singular value decomposition has numerous applications in statistics, machine learning, and computer science. Applying the SVD to a matrix is like looking inside it with X-ray vision. So what we are doing here, we are looking into the given data set with a X-ray vision. So that is nothing but SVD. So SVD with the SVD can be calculated by calling the SVD function. We have in NumPy, not NumPy, SciPy, we have this SVD, and with the help of Python, we can go for calculating the U, S, and V. U is a matrix, S is another matrix, and V is another matrix. Here we are not sigma is we are representing it. Yes, S also represents like singular diagonal matrix. So this is regarding the SVD. we have discussed about dimensionality reduction, right? Okay, right.